Okay, this is where we left off in the previous lecture, the mass conservation equation, which is basically the rate of change of density, dou rho by dou t with time, plus divergence of rho u is going to be equal to 0. So this is the mass conservation equation. Now, as I remarked in the previous lecture, we are going to use the principle of conservation of mass and momentum to basically come up with the wave equation. So momentum obviously means we have to consider forces, and the forces here are basically the acoustic pressure induced. So what I have here is I've used the capital P, which is basically involves the mean pressure plus the acoustic pressure fluctuations that is acting on this infinitesimal volume, dx dy dz. Now the pressure changes from from x to x plus dx. So again we do a Taylor series expansion. The force, of course, on the left, see, as I said, the pressure is considered positive, acting in the direction that is shown. So on each face pressure is positive, compressing it, right? So compression is considered positive. So the force on the left is P times A, and the force on the right is basically P plus the Taylor series expansion of P at basically x plus dx. We are saying is P at x plus dou P by dou x into dx. So that is a Taylor series representation. So if you sum up these things, then the net force corresponds to the acceleration of the fluid in that direction, right? And the mass of the fluid is basically rho times ux, the mass flow rate rather, rho ux. Acceleration will be dou ux by dou t. So rho dou ux by dou t is the acceleration per unit volume multiplied by dx dy dz. You get dou by dou t of rho ux, which is, this is the inertia term. So this is simple Newton's second law, which says that the net forces will be equal to the acceleration. Please remember that since it is compression, that you have we are assuming acceleration is positive that way, but the net force is actually the other way, in the other direction, because this, if you assume dou p by dou x dx is in this direction, the acceleration is in the positive x direction. So therefore we have dou p by dou rho ux by dou t equal to minus dou p by dou x because of the direction associated with that. So this leads to this equation in one direction. You could do this same thing in the other directions, y and z also. So in this case, for the y direction, I will have what will I have? Where is y? Yeah, here. The area that we are looking at is sorry, this is the z direction. The y direction is this way. So the areas that we are looking at is basically dx dz, and the for the z direction it is dx dy, which is this way, right? So we have, sorry, yeah, that is the y direction. Y is upwards, so that is dx dz, and dx dy, which is this way for the z direction. Now so the forces, net force, you can arrive at in a similar fashion. So on the right side and the left side, the top and bottom, all of these you can do. So these forces, remember, have directions associated with that. So effectively the forces in various directions, I have the net force acting in the x direction is minus dou p by dou x, in the y direction is dou p by dou y, and dou p by dou z in the z direction. So I put the unit vectors I, j and k, so that's the total force. And similarly the inertia forces for each of these components of accelerations, rho ux I, rho uy j, rho uz k, and so on. So finally when we write, we get a vector equation. This has three components, so it's basically you can break it down into three scalar equations, but in the vector form is dou by dou t of rho u is equal to minus gradient of P, capital P, which is the total pressure. This is called as the Euler's equation. So this comes from the blue box, represents the momentum conservation equation. We remember you had dou by dou t of rho u plus divergence of rho, sorry, dou rho by dou t plus divergence of rho u equal to 0. That's a scalar equation. Even though there is a vector operation there, you are taking a divergence, which is a dot product. Here it is a gradient operator that comes, so this is a vector equation. So effectively, if you think of this, so I have three equations from momentum and one equation from mass conservation, right? So this comes from these two. So okay, now what else is needed? So effectively we have, let's look at what is the scenario that we have. So we have two equations, two, I should say strictly, mm, if I consider u vector as one variable rather than look at ux, uy, uz, maybe we look at it as ux, uy, uz, in which case I have ux, uy, uz, I have rho, which is another variable, and p, capital P, which is the pressure. Five variables, and we have how many equations? Three scalar. The vector equation, momentum equation, can be broken down into three scalar equations, and of course mass gives you one equation, so we have four equations, right? Now so that means we need one more equation to basically have five equations, five variables. We'll come to that. The thing that you have to remember is that the density rho is actually some mean density rho naught plus rho bar, which is the acoustic pressure density fluctuations. Similarly, the capital P is P naught, which is the mean atmospheric pressure, plus small p, which is basically the acoustic pressure fluctuations. Remember, in the wave equation derivation, we assumed that, we basically assumed that the quantities were small. So that means rho bar in relation to rho naught is small. Similarly, small p in relation to capital P naught is small. So these are the things that are assumed. And u, which is the particle velocity vector, amplitude is also assumed small, and we are not going to consider mean flow effects. So that means these are small perturbations that we are going to look at. So I remarked that if I look at ux, uy, uz, rho and p, I have five variables and we have only four equations that are available. So therefore we need one more equation, and we use thermodynamic relations to basically generate that equation, so that we can now come up with five equations and five unknowns, right? And what we are going to do is actually the wave equation, even though we have five equations, finally the wave equation is going to involve only one variable, and we will derive that as we go along. So basically we need thermodynamic relation. That's what we are going to use, right? Okay, now where does the thermodynamics come in? We are going to look at the fact that the way that we are going to do this is to say that look, the wave propagation is an adiabatic process, we said. Now don't ask me at this stage why are we assuming it is an adiabatic process. I alluded to the fact that Newton assumed it was what do you call isothermal, which was proved wrong. And where does that proof come from? Just bear with me, I will show you why adiabatic assumption is correct. But if it is adiabatic, then you have from your knowledge of thermodynamics the PV to the power of gamma. Remember what is V? V is the specific volume that we are going to look at, and specific volume is nothing but 1 over density, right? So you start with the equation PV to the power of gamma equal to constant. So the small v, which is the specific volume, is essentially 1 by rho. So the way to look at this is to say that, so I can rewrite, let me see if I can open up let me open up, write that equation. So okay, run yeah. So here we have P, capital P, and if you remember PV to the power of gamma equal to C. This is what we have. So this V is specific volume. What do we mean by specific volume? It is volume per unit. So this by definition, volume is meter cube. Specific volume is always meter cube per kg. So all specific quantities, specific enthalpy, specific whatever is, that kg comes into the picture. So meter cube per kg. that is what you have. So this is the specific volume. So rho is basically 1 over this V. So that is the relation that we have, so which is what we are going to use. So your rho, so that means I can rewrite this as P by rho to the power of gamma equal to constant. Now this will be true. So what we are assuming is that this is true, which is also equal to, so essentially since this is true for all states, so when I look at the no wave going through this, then I have P naught and rho naught are the densities and pressure, acoustic pressure, mean atmospheric pressure. So nothing, no acoustic disturbance is there. Then I have this. And when it is disturbed, I have P and rho. So the adiabatic process basically obeys that P by rho to the power of gamma equal to P naught by rho naught to the power of gamma. So let's go back to the slide here. So that is how I get this equation. So this equation came from the fact that P by rho to the power of gamma is P naught by rho naught to the power of gamma. We are redoing that. Now what we do is we substitute P equal to P naught plus P and rho equal to rho naught plus rho. So if I go back into that equation, let me go back to my journal here. Let me insert new page. So let me change the ink color to possibly blue. So I have P is P naught. So I have P naught plus P by rho naught plus rho to the rho bar, right? So that is what we are using. Rho naught by rho bar to the power of gamma equal to constant, which is of course equal to P naught by. So we'll do a binomial expansion. So when you do a binomial expansion of this, so when you look at this quantity, so what does this become? In a binomial expansion, this effectively, so I have P naught plus P multiplied by, if I now look at that as a binomial expansion, I have rho naught so if I can pull out rho naught to the power of gamma in this, and I have a rho bar by rho naught, right? So that is, remember that rho bar is very small compared to rho naught, so I can do a binomial expansion. So I can say that it is rho naught power gamma, and then multiplied by the first order expansion for this will be 1 minus gamma rho bar by rho naught, right? So this is coming from that binomial expansion. So if I pull out rho naught to the power of gamma, I'll have 1 plus rho bar by rho naught to the power of gamma, which of course at the bottom it will be a 1 plus gamma rho bar, and if you invert it, of course you know that it will turn sign into a negative sign, right? So this is an approximation that we have. This is approximately P naught, this should be rho to the power of minus gamma here, right? So that is at the bottom. So I have P naught, which is approximately equal to P naught by rho naught to the power of gamma. So if I now look at these, so you can see that the various terms. So now what we do is when we look at the product that has taken place here, when we do the product, we are going to retain only terms of first order. That means remember that P is considered small, rho bar is considered small. So if I take a product of P and rho bar, I will throw that away because it's a second order thing. So let's insert one more page here. Maybe do that here. Let's say which is equal to, so that is we have P naught by, so the first term will remain as it is, P naught by rho naught to the power of gamma. So that will remain as it is. So that comes from that. And then we have plus we'll have a P by rho naught to the power of gamma, so that is going to be there. So this is, P naught plus P by rho naught to the power of gamma multiplied by this. Then you are going to have second order quantities. So the only thing that we are going to retain is minus gamma P naught rho bar. So rho bar we are going to maintain divided by rho naught. So that we are going to maintain. Of course, everything has a rho naught to the power of gamma, right? So that we'll keep that always there. So there is also a rho naught. So I can say that it is rho naught to the power of gamma plus 1 if you want. Okay. The other term that you will have is P into gamma rho bar, that we are going to throw that out. So if you now look at this, and this will cancel effectively. So what we have is now a relation. We are saying that this is 0. Of course, rho naught gamma is common for all this. So what does it give us? It tells us there is now a relation between rho bar and this. Let me put that in the new page here. So I have P divided by rho naught to the power of gamma equal to, so if I now equate the two, I have gamma rho bar by rho naught to the power of gamma plus 1, right? So let me check that. So here I have dropped out these two terms. I have P naught by rho naught to the power of gamma minus gamma P naught, so I missed out the into P naught here, so I should have P0 here. Okay, so of course I can throw this and what I will be left with is effectively now only a rho naught here. So now we have a relation which says P equal to the acoustic pressure and density are related, which of course intuitively you know that if I have compression, I know density will increase. If I expand, it will decrease, and we now have a linear relationship here, which is gamma P naught by rho naught multiplying rho bar. So this is the relation that we have. The acoustic pressure density, acoustic pressure fluctuation amplitude small p is related to density, acoustic density fluctuations rho bar by this constant, which is the mean atmospheric pressure and density, and this gamma is of course the adiabatic coefficient associated with air, which is 1.4. So it turns out that this particular quantity is equal to what we call as c square, which is where c is the velocity. C is basically the velocity. This is the c is actually the sound speed. So c is basically the sound speed square. So now we have a this is of course depends on what is P naught and rho naught. If you look at typically the pressure at normal atmospheric pressure at sea level, which is about 1 bar, slightly over 1 bar, and the rho naught is about 1.2 kg per meter cube. So if you multiply this, it turns out C is about 343 meters per second. So this is the key indicator that you have to keep in mind. Let's go back to the slides here. So I've gone through the math behind this to show you this. So effectively you have P equal to C square into rho bar, which is gamma P naught by rho naught. 1.013 bar is to be very precise. 1.23 kilogram per meter cube is very precise. Then it turns out C equal to 340 meters per second. Now here is where so the C came from assuming that it is an adiabatic process. So the gamma came from the adiabatic process. Now if I had an ideal gas and temperature was isothermal, if I had temperature constant, then we have, instead of gamma, we have essentially P by rho equal to a constant, right? PV equal to RT. So that is your ideal gas equation. Remember, V of course specific volume, so that I can say P by V equal to RT. If temperature were the same, then P naught by rho naught will be equal to capital P by rho. And if you do the calculations, the gamma factor is not going to be there. It simply says that it is going to be P naught by rho naught. The velocity C isothermal assumption is without the square root of gamma, which is about 1.2. So you can see that the velocity with the isothermal process that is predicted is about 20% lower than what is predicted with the adiabatic assumption. So this is about 340, so 20% of this would mean something like 260 or 270 is being predicted by the isothermal. So this is what Newton had predicted, and unfortunately people do measurement of speed of sound, which is very easy. There are various ways. So I ponder about this. How do I find out that this is 340 meters per second? What kind of experiment I can set up to measure the sound speed? I leave it to you to visualize that. Remember that this can be a quiz question. but it will always be good to ask these questions. So how did people measure the speed of sound and say yes, it is 340, close to 340 meters per second, and therefore the assumption of adiabatic process is far better than assuming that it is an isothermal process, right? So you can see, so when these assumptions are made, the only way that we can check is by going out and making observations. So the way Newton was invalidated, Newton's assumption was invalidated, the isothermal assumption came from measuring the speed of sound in air. So think about how I will carry out an experiment measuring the speed of sound in air. I will leave that as a thought for you. So good. So essentially, we have now a relation. So what happens is that we have used the thermodynamics. So out of the 5 quantities that we started with, we had P, rho bar, the U, so with 3 variables, 3 components. So out of that, now we have established a relation between P and rho bar. So we can go back to those 4 equations that we had. So that is what we will do. So from the fact that the acoustic pressure perturbations are related to acoustic density fluctuations through this c square, which is the speed of sound. So let's go back to that equation, wave equation. So if you go back to that wave equation, remember the wave equation was this. Let us open a new page here. Here. Okay, so here remember that we had dou rho by dou t plus a divergence del dot rho u equal to 0. So this was my mass conservation equation, right? So if I now look at this equation, rho is going to be written as rho naught plus rho bar. So you see that dou rho naught by dou t will be 0, will be equal to 0 because rho naught is the mean density, so this doesn't change with time. So this equation essentially boils down to which is simply going to be dou rho bar by dou t. Now if I look at this term here, I will have rho naught u plus I will have a rho bar u. Remember we are assuming all these quantities, both u, rho, rho bar are all small quantities. So therefore what we are going to do is to throw this out. So effectively this particular term simply becomes, so this becomes effectively gradient. So since rho naught is not varying, so it will simply become a gradient of velocity. Sorry, a divergence of velocity. So del dot u is all that it is going to become. So I'll put the dot there. So you can see that this simplifies to dou rho bar by dou t, and this simply the mean density alone comes out, and you have the divergence of velocity. So this is what happens. So let's go back to our slide here. Therefore, the equation, momentum conservation equation, simply becomes, and remember, what is rho bar? So we are going to throw out rho bar. We only want to keep pressure. So if I go back to my little thing here, this rho bar, remember, is p square by c. I think, where was that? Okay, so let me go back here. Now let's so we'll replace this rho bar. Rho bar is going to be, remember, p equal to c square rho bar. So therefore this will be, so one way to look at this is to say I can replace this and write it as dou p by dou t by c square. So this will become, let me draw a line arrow here, probably choose a slightly different thing and then write this as 1 by c square dou p by dou t. Okay, so we can eliminate rho bar. This comes from the thermodynamics, so we can eliminate that rho bar. So you got that. Of course, what do I have? This is the momentum. Sorry, I have gone one step ahead and replaced that already here. That's fine. So which is okay. So that's, I guess, I've gone one step ahead. And basically the mass conservation equation, now I have only p and u, and in the momentum equation again you can see the dou by dou t of rho u that I have, we will drop out. Basically I had the acceleration term, the inertia term was dou by dou t of rho u, so I have a rho naught u plus a rho bar u bar u. The rho bar u we throw out, so we'll have a rho naught dou u by dou t, which is the acceleration term, and this is the gradient of pressure that will come again. So okay, so finally if we take the I think that it's better to eliminate this. So I have two equations, so the following equations, let's go back. So let me write put out a new slide here, new page after. So what we have is the following equations. Mass conservation gives us 1 by c square dou p by dou t plus rho naught del dot u equal to 0. So this is from mass conservation, right? The momentum conservation equation simply is rho naught dou u by dou t. So this is the inertia term plus gradient of acoustic pressure fluctuation equal to 0. So this is momentum and this is mass. So you can see that one of the good things now is that I have this is 3 equations, this is 3 and this is 1, and how many variables do we have? Ux, uy, uz and p. So therefore 4 equations, 4 unknowns we can solve. So the way we do this is to basically eliminate. So what we do is we now eliminate, we want to eliminate u. So we basically want to get rid of u. So remember, u and p are related through this. We can kind of use this. So that we are going to do. And when we do that, let me go back to my slides. I will show you what we have done here. So if we take the divergence of the momentum equation, that means so if I do so this, let me call this equation 2 and this is equation 1. So we do a del dot 2. So that is what we are going to do. So therefore it becomes rho naught dou u by dou del dot dou u by dou t, and we can interchange the order of the derivatives. So I can say it is rho naught dou by dou t of rho naught del dot u, so which is nothing but this equation, and here I have del dot del p, which is del square p. So if I now use this equation to eliminate, so what I will do, so when I do this, I will have, let me go through that derivation in a new page after. So let me go through that. So when I take that del, so what I will have is, I will have, let me erase this. So I will have dou by dou t of rho naught del dot u plus divergence of gradient, so that gives me the Laplacian operator del square p equal to 0. So here we are assuming we can interchange. Basically we are saying that interchange. We can interchange order of the operators. So that is being assumed here. So the order of the operators we are assuming that can be interchanged. So the del dot rho naught del dot of rho naught dou u by dou t, we are saying is dou by dou t of rho naught del dot u. So that order interchange is there. Now if you go back to the previous page, you can see here that rho naught del dot u is minus 1 by c square dou p by dou t. So if I substitute that, essentially this now gives us the wave equation, which is del square p equal to 1 by c square dou square p by dou t square. So you can see now I have a complete equation only in terms of the pressure variable, which is, remember why we want it in terms of the pressure variable, because the measurements that we talked about in the previous module were all acoustic pressure. That's the most easy to measure, right? In fact, for particle velocity we had to do this pressure gradient. So that if you were wondering why I had to do a pressure gradient, let's go back to this equation. You see the acceleration of the particle dou u by dou t is related to the pressure gradient, right? So if I look at it as a finite difference approximation, the dou p by dou x is nothing but delta p by delta x. That is why we were using in the intensity measurement when I wanted to look at the velocity component. I basically used the gradient to arrive at that, right? So now you can see why the intensity, which is P times U will be obtained through that Euler equation, right? So this is the wave equation. All right, let us go back to the slides here. So this is the green box is the equation that we are going to deal with. So this is called as the wave equation. I think this will be a good place to stop this video. So we have derived the wave equation, which basically says the del square, which is the Laplacian operator, Laplacian of P, equal to 1 by c square dou square p by dou t square. So this governs basically the acoustic wave equation. We'll in the next video we will see how do I solve this so that I can get an insight into the kind of behavior that this wave has, properties that this wave has. Alright, we will stop here and then we'll continue with the solutions from the next